Okay, okay, so I'm gonna throw it up here from last time, and we'll just take a look at it on the screen. So it has to do with intermediate value theorem. It's well named. It does what it says. Where is our stuff from last time? Hang on. Okay. So here's our stuff from last time. Let's pop up to the intermediate value theorem. There we go. Okay. So this is a pretty good slide, right? So the intermediate value theorem just says if we have a function that's continuous on a closed interval from a to b, and if n or k or whatever that book calls it, if n is an intermediate value, meaning it's between the values of the function at the left and right endpoints, if it's in between there somewhere, if all that stuff is true, then IVT guarantees there's going to be at least one place on that interval between a and b where the function passes through that intermediate value. Okay, and there might be multiple, okay, but the only thing that has to be true there then is the function has to be continuous on that closed interval, and that's criterion 1. Criterion 2 is that n is an intermediate value, so it's somewhere between f of a and f of b. This is a useful one for us for many reasons, but oftentimes it's a way to prove that there's a zero or a solution to a function, right? If we know that a function is positive valued at one endpoint and negative valued at the other endpoint, doesn't matter which is which, then, and the function's continuous on that interval, then it has to pass through zero. So we know there'd be the existence of a zero there, okay? All right, so Cahill, why don't you impress us with your logic here? What's the... Yeah, go for it.
So if you like, so 20 minutes up, like going up, so
Mm-hmm.
he goes up, like, it takes him like 15 minutes to go halfway.
Mm-hmm.
He only has 5 minutes to, he goes up 5 minutes.
Okay.
So if you just divide this one by half, 5 minutes, 5 minutes, the first 5 minutes will be the same as these first 5 minutes.
Okay. Mm-hmm.
You get the same for top half.
Okay. Okay. I'll take it. Anybody want to give me another argument there? Maybe don't even use IVT. Can you just use logic to demonstrate that he has to pass by the same place at the same time? Any ideas? All right, so now the thing that makes this a little bit tricky to think about is the fact that it's happening on 2 consecutive days, right? The trip up is on Saturday, the trip down is on Sunday, right? Would it be easier to think about this in terms of a single day maybe, right? What if you had 2 different people? One of them is he's just representing himself on both days, squeezing that into one day. If he leaves here at 8 a.m. and gets to the top 20 minutes later, this guy leaves at 8 a.m. and gets down there 10 minutes later, wouldn't they obviously have to pass by each other at some point, right? If that's true, then the fact that they're separated by a day doesn't really matter, does it? Because you're looking at your time on a watch. So there's maybe a logical way to look at it. How could you do it with the intermediate value theorem? Any ideas? What do we have to do here? We have to define some function, and it's got to be continuous on this interval, right? So the interval here is going to be, let's say, between 0 and 20 minutes, right? And there has to be some intermediate value to the function, right? The function has to pass through some intermediate value between the value at 8 a.m. and the value at 8:20. Okay, so one way we could do this is kind of cool. One way we could do this would be to define some kind of a position function. If we let s of t be the position of this person for the run up the mountain, Okay, it's starting at 0 and ending up at whatever, I don't think they tell us what his distance is, you know, whatever it is. It starts at 0 and it ends up at, let's say it's half a mile or something, right? It ends up at half a mile, okay? If we let r of t be the position function for the run down, it starts at half a mile and ends up at 0 10 minutes later, right? Anybody good with that? Give me thumbs on that. Is that good? Okay, so let's define some function that joins those, some function f that's going to be the difference. It's going to be s of t minus r of t. So at 8 a.m., we'll call that time 0. We're starting our stopwatch. What's the value of s of t? At 8 a.m., person that's starting down here. 0, okay? At time 0, at 8 a.m., what's the value of r of t? Half a mile, right? If we're saying it's a half a mile hike, okay? So then 0 minus 0.5 gives me negative 0.5, okay? What about after 20 minutes? 20 minutes later, what's s of 20? Half a mile. What's r of 20? 0, right? Okay. So 0.5 minus 0 is 0.5. Started off, this function f had initial value of negative 0.5, had a final value of positive 0.5. Is the function continuous? To ask if f of t is continuous, you just have to ask, well, are s of t and r of t continuous? Because if they are, f of t has to be, right? Is s of t continuous? Has to be, right? You can't, I mean, he can't, we don't live in a macroscopic quantum universe where he can just blink from one place to another place and, you know, one moment he's here, next moment he's there. He has to pass through every distance continuously between 0 and 0.5, right? Same thing here. Coming down, this guy has to pass continuously through every displacement from 0.5 back down to 0. So the function is definitely continuous from 0 to 20 minutes. What would be the value of f when he passes by the same place at the same time? It'd be 0, wouldn't it? Right? When he's passing by the same place, s of t and r of t would have the same value, be the same distance from the start, right? So that works, doesn't it? That meets the criteria of the intermediate value theorem. We've got some continuous function, continuous on the interval from 0 to 20. The initial value, so at a, which would be t equals 0, it's negative. At b, which is t equals 20, it's positive. So therefore, it must pass through at least once, in this case exactly once. It's got to pass through the intermediate value of 0. Just proved it. By IVT, this has to happen, right? Everybody see that? Give me 1 to 5 on that. How are we doing on that concept? Okay. All right. All right. So what I want to do today, I just want to take a little time, and this is, to me, this is a really fun part of calculus. This is one of those parts where, how many people are in physics? Okay. So this is going to make more sense initially if you're in physics, but even if you're not, it's okay. I mean, these concepts aren't, you're familiar with these concepts and this vocabulary. This is kind of a good one because it's the first time that you really get to join math to something real world that's actually not hokey. I mean, where it really does something important, I think, in your entire career in math. So let's talk about kinematics for a second. So kinematics is just the study of motion, right? We're just quantifying motion. So the kinematic quantities are position, velocity, and acceleration that we'll talk about, right? And we're going to write those all as functions of the common independent variable t, okay? So position is going to be, we're going to call that, we'll just call it x of t. We're going to restrict ourselves here to really simple motion. The motion is just going to be along a straight line at the front of the room, one-dimensional motion, okay? So position function, you know, if it's horizontal, it'll be x of t. If it's vertical, it's y of t. Or more generally, you could just call it s of t. If there's no, we're not specifying a direction. It could be any direction. But we're going to stick with x of t. So average velocity is just change in position over change in time, right? When we put a bar over something, it means average, okay? So average velocity is just change in position, which you guys call, what do you call that in your physics class? Change in position. Displacement, right? Okay, so displacement is change in x over change in time. Okay, there's average velocity. Average acceleration is just change in velocity over change in time. Okay? Let's talk for just a second about what kind of quantities are these. So we've got two kinds of quantities in math and physics that we like to talk about a lot. We've got scalars, a scalar quantity, and man, this pen is really starting to give up the ghost. Vector quantities. Okay, so those of you who are in physics, remind us what those are. Okay, so scalar, there's only one part of a scalar. Okay, so a scalar is, it has just a magnitude or a number. So an example of a scalar quantity would be like the temperature in the room. All we need is a number for that, right? Or if you were, like what page are you on in a book? That could be considered a scalar quantity. All that it needs is a number. Speed is a scalar quantity. If you're driving in your car and I wonder how fast you're going, where do you look? Look at the speedometer, whatever it says, that's telling you a reading of your speed. You don't need anything else, right? You don't need a direction. I could be going 50 miles an hour traveling in any direction and still I'm going to say my speed is 50 miles an hour, right? So that's a scalar. Okay, what about vectors? Vectors have two parts. They have a magnitude. Just like scalars, we need a number associated with them, a magnitude. How big is this quantity in terms of a number? But this time they also get a direction. Okay, so vectors are associated with a specific direction. Okay, these are vector quantities, so I really should put a vector hat over these. Okay? And acceleration, we would just call that A with a vector hat. Okay? What's that vector hat? It's just supposed to be kind of like an arrow, right? Which remind us that they have a direction. Okay? So let's take a little example here, a little reminder about what these things are. If I take the example, what happens if I delete that? Oh, I don't want to do that. Everything goes away. There we go. Okay. Yeah. Okay, so if I want to tell a little story up here, these kinematics diagrams are going to do that for us. So what's this telling us here? I'm plotting position is my dependent variable as a function of time in seconds. So maybe position in meters as a function of time, right? So what does this look like? Well, I'm starting off with a position of -1, and 2 seconds later I've got a position of +1. Well, let's just say that this is the starting line. This is 0, how about, right? And this is the only direction I can walk in the positive x direction. So we're calling that the positive direction, that the negative direction, just like a number line, like the x-axis. So this is a pretty boring story. All it's saying is that I'm starting here at -1, and my position after 2 seconds is going to be at +1. Okay? What can you tell me maybe about my velocity during that time? Keep in mind, velocity is defined as, if we go back to the previous page, velocity is defined as the change in position over change in time. What do you think? Okay, everybody agree with that? Right? If I look over this interval here, if I were to calculate my change in position over change in time, we're getting velocity equals delta x over delta t. Well, the change in x, that's 2. This is a slope, isn't it? Doesn't that look like a slope? Right? Rise over run. My vertical quantity is x, so that would be the vertical motion would be the rise. My horizontal quantity is t, so that looks like a slope, and I'm just getting 2 meters over 2 seconds. So I get 1 meter per second. Everybody agree? Okay, doesn't that seem like what I just did there too? If I start the camera right now, stop it right now, that's a pretty boring picture. I'm just walking at constant speed. Evidently the speed is 1 meter per second in the positive direction. Okay. So how would I graph that then? What's my velocity graph look like? So there's 1 second. There's 2 seconds. What's that picture going to look like? Yeah, it's just constant, isn't it? Right? V is equal to 1. It's just going to end up being a flat, if that's 1. It just looks like, I don't know what it's doing. There. Just horizontal line. Okay, can we relate those pictures? Well, we talked about slope. Yeah, isn't that true? Isn't the slope of this blue line 1? And therefore, that's the value of velocity, right? Rise over run was 1, so that gave me this value. What about acceleration? What's my acceleration? Yeah, and we know acceleration's the change in velocity over change in time, right? So we're going to come to call that a rate, by the way. Anytime we're looking at quantities that are changing with respect to each other, we call that a rate. But you called slope rate clear back in Algebra 1, right? So velocity is the rate of change of position. Acceleration is the rate of change of velocity, right? Okay, this is pretty, it's got a slope of 0. My rise is 0 on this function when my run is 2. And so the velocity, or excuse me, the acceleration function just looks like that. It's pretty boring. I'm not accelerating. My speed is staying the same. Okay? We'll come back and we'll look at some more exotic, more exciting stories than this one, but I just want to introduce this relationship between these kinematic concepts. Okay, what about that one? Let's maybe look at just one of these real quick. What's going on there? And we'll come back and discuss this in way more detail, but see if you can just make a guess here. If that's my position versus time graph, okay, why? You're right. Why? Not a straight line. Okay, so if I were to look at just a couple little intervals on this, like if I wanted to calculate my average velocity from here out to here, right, well, I'm going to rise by a certain amount, and I'm going to run by a certain amount, and that would be the slope that connects those 2 points. So I've got a certain average velocity between the start and that point right there. Right? If I started it, let's say I start the clock again here, and so I'm going to look at the interval from there up to there. Well, if I calculate that rise over run of that little increment in time, it's a little bit steeper, isn't it? Right? So I've got a little bit higher velocity, and then even more so up there if I took that last little piece, right? So we kind of get an idea here that the slopes of between any 2 points on this dark blue position graph are getting steeper, and so I should expect maybe the velocity to get steeper. What do you think the velocity graph might look like then? What's it starting off at right there? if I took say it again. Everybody see that? If I took a really short interval, the slope would be very small, right? It'd be close to 0. So I'm going to start off down here with a velocity of 0. As I move along, the slope is getting higher. So the velocity function might end up looking something like that. It's just increasing with time. Okay? Well, what does that tell us about the acceleration then? The acceleration here is positive this time, isn't it? It's not 0, it's positive, right? This has got a constant slope. And so the acceleration function kind of looks like that. Okay, where we're going with this, we're almost out of here, aren't we? Where we're going with this is, what we want to do next time is we want to take these average quantities and start to convert them into instantaneous quantities. And that's where we need some calculus, okay?